Welcome to section 4.1, linear equations. So in chapter 2, we explored methods for solving certain first-order differential equations by identifying them as separable, linear, exact, or possessing homogeneous coefficients. While these techniques allowed us to find solutions expressed as a one-parameter family, these solutions, except in one case, did not always represent the general solution of the differential equation. So a general solution is a family of solutions defined on an interval that includes all possible solutions of the differential equation within that interval. The only case where we successfully obtained a general solution was for linear first-order differential equations, provided that specific continuity conditions were met for the equation's coefficients. So as we move into higher order DE equations in this chapter, our primary focus will be on finding general solutions of linear differential equations. So to achieve this, we must first develop a foundational understanding of the theory behind linear equations, which will guide our approach to solving them systematically in this chapter. Objective number 1. So understand the difference between IVPs and BVPs. So that's initial value problems and boundary value problems. So in section 1.2, we were introduced to IVPs for DEs, and a linear differential equation of order n was provided to us in this format, where you have a sub n all the way down to a sub 0 of x of y equals g of x. And then we were given initial conditions. So we had y of x sub 0 equals y sub 0, and then we may have had y prime of x sub 0 equals y1, and then so on and so forth. So this means we are looking for a function y of x that satisfies both the differential equation and the initial conditions at x sub 0. So for second order initial value problems, the solution curve then must pass through a point x sub 0, y sub 0, and have a slope y sub 1 at that point. Okay, so in addition to that, in section 1.2, we also discussed the conditions under which an IVP has a unique solution. And if you recall, theorem 4.11 that states that a unique solution exists if the coefficients are continuous over the given interval I, and the leading coefficient does not equal 0 for all x and I. Because if the leading coefficient a sub n equals 0 for some x, a unique solution may not exist, or the solution might not exist at all. So if we consider this second order IVP, a squared y double prime minus 2xy prime plus 2y equals 6, and its initial condition, y prime of 0 equals 1, a general solution to this equation is y equals cx squared plus x plus 3. Now, since the parameter c is arbitrary, the solution is not unique. So the issue then arises because a sub 2 of x equals x squared, right? And we got that from our DE, all right? Which equals 0 when x equals 0. So if we were to substitute in 0, a sub 2 of x would equal 0. And this is the same point where the initial conditions are applied, because we know y prime of 0 equals 1. So this violates the conditions required for the uniqueness theorem in 4.1.1. Okay. Unlike IVPs, boundary value problems, or BVPs, involve conditions specified at different points rather than at a single point. So a second order BVP takes this form, so a sub 2 of x all the way down to a sub 0 of x equals g of x. And this is subject to boundary conditions where you have y of a equals y sub 0, or y of b equals y sub 1. This is called a 2-point boundary value problem because conditions are specified at 2 different points. So that's where x equals a or x equals b. And these conditions, known as boundary conditions, ensure that the solution curve passes through both points A, y sub 0, and B, y sub 1. Okay, so that's the difference between the initial value problems and the boundary value problems, and looking at it in first order and second order. Objective 2, so understanding the difference between homogeneous and non-homogeneous DEs. So a homogeneous linear differential equation, as we know, is one where the function and all its derivatives appear in the equation without any additional terms. So in simpler terms, if all terms in the equation involve only y and its derivatives multiplied by functions of x, and the equation equals 0, then we know it's homogeneous. So for an nth order linear differential equation, the general form is written here. It's the same one we looked at in the previous chapter, in chapter 2. So since the right-hand side is 0, then we know that the equation is homogeneous. One other important fact about homogeneous equations is that y equals 0 is always a solution. On the other hand, non-homogeneous differential equation involves an additional function g of x on the right-hand side. It's the difference between the two, and g of x then does not equal 0. So for example, an homogeneous equation would be 2y double prime plus 3y prime minus 5y equals 0. So this would be considered a linear second order DE. And a non-homogeneous would be x cubed y triple prime plus 6y prime plus 10y equals e to the x. Here our g of x is e to the x. This equation would also still be considered a linear DE, but a third order DE. So a key principle in solving non-homogeneous equations is that we must first solve the associated homogeneous equation before tackling the full problem. Okay. All right. Objective number 3. Recognize the role of differential operators. So this is something that you probably may have seen in calculus. This will appear throughout chapter 4. So we're just going to refresh our memory with this operator. So in calculus, differentiation is often represented using the differential operator d, so capital D, where capital D times y equals dy over dx. So in other notations, you might see capital D squared y, which is the second derivative of y, with respect to dx. Then you can get other higher order derivatives like capital D to the fourth. So that would be the fourth derivative of y with respect to x. So for example, the differentiation rules in operator form look like capital D times the cosine of 4x. So that's the derivative of cosine 4x, which would get us negative 4 times sine 4x. Or we may have the differential operator of 5x cubed minus 6x squared, which would be 15x squared minus 12x. We can also define differential equations using differential operators. So in this example here, we have d squared plus 5d plus 6 all times y equals 5x squared. We would write this instead of writing y double prime plus 5y prime plus 6y equals 5x minus. The differential operator just makes solving equations more systematic. So the general nth order differential operator can be written in this form. So this is just a formula depending on the highest power to which your differential operator is set, all the way down to your constant a sub 0 of x. So using this, we can compactly represent linear equations as L of y equals 0, which is a homogeneous case, or L of y equals g of x, which is a non-homogeneous case. Our differential operators also follow linearity properties if c is constant. So the differential operator of c times f of x would be the same thing as c times the differential operator times f of x. Or if we have the differential operator of the sum of f of x and g of x would be the same thing as the differential operator of f of x plus the differential operator of g of x. These properties then also apply to the operator L, making it a linear operator. So if we're now multiplying f of x and g of x by a constant, we would take the constant times the linear operator times f of x plus the constant beta times the linear operator times g. So all of the properties of linearity that we already know and use can be applied as long as c is a constant. All right, objective number 4. Applying the superposition principle to construct general solutions. So one of the most important results for homogeneous linear DEs is the superposition principle. And the superposition principle states that if y sub 1 of x and y sub 2 of x are both solutions of a homogeneous linear differential equation, then a linear combination can be formed. And that would be y equals c sub 1 times y sub 1 of x plus c sub 2 times y sub 2 of x. And it continues on depending on how many other solutions you have for your homogeneous linear DE. And this would be considered a solution on the interval where C equals, again, the constants present in your solution, depending on how many solutions you have to your DE. Okay, so to make this, click a little bit, let's do an example. So we're going to consider this homogeneous equation, x cubed y triple prime minus 2xy prime plus 4y equals 0. And the two solutions for this equation are going to be y sub 1 equals x squared and y sub 2 equals x squared natural log x. So we have two solutions to this homogeneous equation, one identified as y sub 1 and the other identified as y sub 2. So by the superposition principle, the linear combination then would be y equals c sub 1 x squared plus c sub 2 x squared natural log x. So the x squared represents the y sub 1, which is the first solution, and the x squared natural log x represents the y sub 2, which was the second solution. So we have now created a linear combination, which is a solution to our homogeneous equation. Okay. Let's look at another example. Say we have the function y equals e to the power 7x is a solution to the DE y double prime minus 9y prime plus 14y equals 0. So since the equation is linear and homogeneous, any constant multiple of this function, such as y equals c times e to the 7x, is going to be a solution. So we can choose different values of c and give different solutions to our DE. So if we substitute or identify C as 9, we then get y equals 9 times e to the 7x. Or if we identify C as 0, then we get y equals 0, which we know is going to be a solution because it's homogeneous. So y equals 0 will always be a solution. And then y equals negative 5e to the power 7x would set C equal to a negative 5. And all of these solutions are going to satisfy the DE equation. So this principle allows us to construct general solutions from a set of independent solutions. Objective number 5. Determine whether a set of functions is linearly dependent or independent. So a set of functions is linear independent on an interval I if the only constants that satisfy c of 1 f of 1 of x plus c of 2 f of 2 of x plus all the way down to c of k f of k of x equals 0 for every x on the interval where all of your constants equal to 0. Otherwise, if it's not linear independent, then it would be linear dependent, meaning at least one function can be written as a linear combination of the others. Okay. So in computing, the Warkins provides us a test for linear independence. So the Warkins, and I'm pretty sure I'm pronouncing that incorrectly, but hopefully I'm not, determinant when used, allows us to run this test. So let's say we have two functions. Again, you might have 3 functions, 4 functions, but for this case, we're just going to have 2. And they're given by f of 1 of x and f of 2 of x. So we're first going to substitute both functions into our Warkins test. And when doing this, we're going to create a matrix, our determinant. So in the first row, we're going to list all of our functions. So since we have 2, f of 1 of x and f of 2 of x are in the first row. If you had 3 or 4, you would list all of them out. Then in the second row, we would take the derivative of each function. So the first derivative of f of 1, the first derivative of f of 2, and then if we had others, it would be f of 3, f of 4, and so on. Now, we want to create a determinant, so we want to have a square matrix. Okay, so if we had 3 functions or 4 functions, we would want to make sure that we had a 4 by 5 determinant, so we would continue the derivatives until we reach that square matrix. Then we would use any formula that you know of to find the determinant. It depends on what courses that you've taken prior to this class. And so since we have a 2 by 2, I'm going to cross multiply. So I'll multiply my f of 1 of x times the first derivative of f of 2, and I'll subtract it from the product of f of 2 times the first derivative of f of 1. So this determinant helps determine if 2 functions are linear independent. So if when we find the difference between these 2 terms does not equal 0 for at least one value of x in the interval, then we know f of 1 and f of 2 are linear independent. But if it does equal 0 for all x in the interval, then they are linear dependent. Okay. So to make this stick a little bit, let's do an example. So let's construct the Warkins determinant for the function sine squared x, cosine squared x, and 1. So in this case, we have 3 different functions here, sine squared x, cosine squared x, and 1. So we're going to enter that into our Warkins determinant. So when we set up our determinant in our first row, we're going to have all of our 3 functions, so sine squared x, cosine squared x, and 1. We are wanting to create a square matrix, so we're going to continue taking the derivatives until we have a 3 by 3 square matrix. So the derivative of sine squared x would be 2 sine x cosine x. Derivative of cosine squared x would be negative 2 cosine x sine x. Derivative of 1 would be 0. And then we would do it one more time, taking the second derivative. Okay. Now, again, using whatever method that you would like to utilize in solving the determinant, since my third row is 1, 0, 0, I'm going to use 1 as my multiplication factor, and I'm going to use the 2 sine x cosine x, negative 2 cosine x sine x, and the 2 cosine squared x minus 2 sine squared x, and the 2 sine squared x minus 2 cosine squared x as my 2 sets of functions that I will cross multiply. So when I do that, so I'll take 1 times 2 sine x cosine x, and across from that would be 2 sine squared x minus 2 cosine squared x, plus, well, the plus comes from actually subtracting negative 2 cosine x sine x times 2 cosine squared x minus 2 sine squared x, so the 2 negatives become positive. Okay, so what I'm doing is I'm multiplying these 2 elements together and then these 2 elements together. Again, each set of elements I'm multiplying by 1. When I now have my elements multiplied, I then get this expression here. So what I now need to do on my next step is to multiply each term by the factor on the outside. And so when I do that, I'll then get this lovely expression. You see a lot of 4s in there, but if you notice, there are some like terms. So we have 4 sine cube x cosine x, and over here we have negative 4 cosine x sine cubed x. So these two terms will cancel out. In the middle here, we have something similar, negative 4 sine x cosine cube x plus 4 cosine cube x sine x. So these two terms are also similar, and so they cancel out. And so we know then that our Warkin's determinant equals 0. And since the Warkin's determinant is 0, this indicates that the functions are linear dependent on the given interval. So this result aligns perfectly with the trigonometric identity sine squared x plus cosine squared x equals 0. We can rearrange this function and we'll see that there is a relationship between sine squared x plus cosine squared x and 1. Okay, because each one can be expressed as a combination of the others. That concludes section 4.1. Enjoy.